This deck of cards is compiled to assist you in working through the MCAT-style passage, the bicarbonate buffering system, and titration curves. Questions dealing with acid-base equilibria are very common on the MCAT, so this is a good step for you to go through. The pH of blood in humans is around blank. So what is the pH of blood in humans? 7.4. It's almost neutral, like water. A rise of physiological pH above blank leads to the condition of alkalosis. Physiological is an adjective describing internal conditions of the human body, and alkalosis is a state of being basic, a pH above 7. So above what pH is considered alkalosis? 7.45. If physiological pH drops below blank, this depression leads to acidosis. Acidosis being the state of acidity. So a pH below 7.35. A conjugate base is the species formed by the removal of blank from its conjugate acid. So what has to be removed to form a conjugate base? That would be a proton or a hydrogen ion, okay? So this is what has to be removed in order to form the conjugate base. And I'll just label the conjugate base as A negative. But together, if they were, to get back together, usually it oscillates between these two states. You would form the conjugate acid. Okay, the equivalence point of a titration is the point where the number of moles of added base is equal to or greater than, what's the best fit? The number of moles of acid in solution. So, I mean, a big hint is equivalence point. So take a wild guess if you're not familiar with this concept. That's equal to. So if you're titrating a weak acid by adding a strong base, like sodium hydroxide, usually the base added in the titration in word, problems is going to be this sodium hydroxide. And here goes your hydroxide. It, completely dissociates in water in aqueous phase. Okay. All right. So when the pH of the solution is greater than the pKa for the proton is removed or remains, and the compound becomes deprotonated at that region. So does the proton get removed or does it remain in association with its conjugate acid? When I say it gets removed, I mean, is it, taken off of its conjugate acid to form the conjugate base? And the answer is it gets removed. And that question, or any question that you might see that looks like that, sometimes gets a little fuzzy conceptually, but it's really a question of the Henderson-Hasselbalch equation, which just basically calculates the pH for a buffer solution. So it's referring to this. pH equals pKa plus, so this is the deciding factor of if a proton is going to get removed or remain in association with its conjugate acid, and it's the log term in the Henderson-Hasselbalch equation. Okay, so it's the log of the concentration of conjugate base. So if this number is really, really big, you know, that's supposed to be an arrow, then that means you have a lot of base in solution. And they're going to want to remove, you know, proton as opposed to the concentration of acid in solution. If this number might be really small, this is when the pH is going to see a dramatic increase. And if the opposite were true, if the denominator, the concentration of acid were really huge and the concentration of conjugate base was really small, the proton would remain in association. It wouldn't be usurped by, you know, a negative anion species. Okay. When the pKa of a solution is less than, well, I said the pKa, when the pH of a solution is less than, there's supposed to be a line there somewhere, the pKa for a proton, the proton is removed or remains at that region. We just slightly discussed this, so what do you think it is? It remains because, again, you're dealing with the log term in the Henderson-Hasselbalch equation. And so you have the concentration of conjugate base in the numerator. And then the concentration of conjugate acid in the denominator. So if this number is really big, you're going to get a tiny decimal for this ratio. And, you know, decimals yield negative logs. So when you add a negative number to the original pKa, it's going to decrease the pH or make the pH less than the pKa. Okay?